In this lecture, I'm going to introduce a new partially ordered set, the lattice of non-crossing partitions. So a set partition X in a set partition of N is said to be non-crossing if for all I strictly less than j, strictly less than k, strictly less than l, four numbers between 1 and n, if I and k, the first and third, are in the same block of X, and if j and l, the second and fourth, are in the same block of X, then all four I, j, k, l are in the same block of X. So the reason this is called non-crossing is that we are somehow saying that the blocks do not cross. If you draw these I, j, k, l in their natural order, then I to k, this is in one block, and you can join them by an arc. J to l, they are in another block, you join them in an arc. Then what you're saying is that the block containing I and k crosses the block joining j and l. And so if you don't want this to happen, then I, j, k, l better all be in the same block. So this is an example of a crossing. But a nicer visual representation is to put the numbers 1 to n in a circle. So let me just show you with an example. Let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And let me just draw some blocks here. So let's say 1, 2, 6, 7, that's one block. Then 3 and 4 is one block. And 8, 10, 11 is another block. Now this set partition, this represents the set partition 1, 2, 6, 7, 3, 4, 5, 8, 10, 11 and 9. Now this set partition is non-crossing, and the way you see this from the picture is that if you look at the numbers which form each block, then their convex hulls are disjoint. So the blocks have disjoint convex hulls. Okay, so let's because this condition for non-crossing involves at least 4 points, for n less than 4, all set partitions are non-crossing. But let's look at the poset of non-crossing partitions of 4. So the poset of non-crossing partitions is the poset induced in pi n. So the partial order is just inherited from pi n, that is the refinement partial order, by the set of non-crossing partitions. Now here I have a picture of the non-crossing partitions of 4 numbers. I have not drawn the numbers, marked the numbers, but if you want you can take this to be 1, this to be 2, this to be 3 and this to be 4. And these are all the non-crossing partitions. We have almost all the partitions of 4 except for one partition which would have been crossing, which is this, which would represent so if I call this 1, 2, 3, 4, then this would represent 1, 3, 2, 4. So except for this, every partition of 4 is non-crossing. Now, in the poset of all partitions pi 4, we saw that we still had these 4 layers, but the second layer had 7 elements, whereas the third layer had only 6 elements. And now somehow this diagram looks a little more symmetric. Now, the first thing I want to show about non-crossing partitions is that they form a lattice. Now, we've seen that if a poset is a meet semi-lattice, that is, any two elements have a greatest lower bound, and it is finite, and it has a greatest element, then it is a lattice. Of course, NCN has a greatest element. The partition where all the elements are in one block is clearly non-crossing. And so we only have to show that it is a meet semi-lattice. And for that, it's enough to show that if x and y are in NCN, then their meet in the lattice of set partitions. So I'll signify that we're taking meet in the lattice of set partitions. This belongs to NCN. And then that will become their meet in the lattice of non-crossing partitions. But this is easy because if I, j, k, l are 4 numbers between 1 and n, and so I want to show that the meet is in the non-crossing partitions, and I and k, j and l, these are in the same block of x meet y in the meet in pi n, then of course I and k are and j and l, well, since each block of the meet of x and y is contained in a block of x, these are in the same block of x and in the same block of y. Which means, since x and y are non-crossing partitions, this means that I, j, k, l are all in the same block of x and all in the same block of y. Which means that they are in the same block of the wedge. Okay, so it's a fairly straightforward proof. But the meet in the lattice of non-crossing partitions coincides with the meet in the lattice of all partitions. But you need to be a little more careful with the join. So if you take the partitions 1, 2, 4, 3 and take the join in pi n with the partition 1, 3, 2, 4. So what I need to do is I need to take the set partition whose blocks are are obtained by taking those elements which are in the same block either of the x or of y. And so this is going to be just 1, 3, 2, 4. Okay, but 1, 3, 2, 4, this does not belong to NC4. And indeed, if you look at it here in this picture, these are set partitions with 2 parts, with 3 parts, and so they are in this layer. And if we take these 2 pictures here, then we see that they don't have any common upper bound in the second layer, and the only common upper bound that they have is the trivial partition. It's just the trivial partition. Now, there's another nice thing about non-crossing partitions which makes it slightly nicer than uh, the lattice of all set partitions, and this is a beautiful theorem of Crevera's, which says that the lattice or the poset of non-crossing partitions is isomorphic to its opposite poset. This is the poset with the same elements but where the order is reversed. Now I'll give you a visual proof of this, a visual construction. So what I'm going to do is I'm going to define a bijection from the set of non-crossing partitions of n to the set of non-crossing partitions of n, which reverses the refinement partial order. So the proof is by a visual construction. Let me just do it by an example, and I'll let you think about why this works. So let's just take a set partition with on NC10, and so let me just take, for example, I'll join 1, 5, 6, 10, 9, 10, 2, 3, and these will be singletons. So what is the set partition? This is the set partition 1, 5, 6, 2, 4, 3, 7, 8, 9, 10. Okay, now I will define its image. So I'll define a bijection, right? So what I'll do is I'll draw the points 1, 2, 3, 4 again, but in between the points 1 to 10 of the old set partition. And now what I'll do is I'll draw the blocks of the new set partition to be the blocks of the old set partition, which are not separated by the blocks of the new set partition. In some sense, the connected components. So for example, 1 and 4 are not separated by the old set partition. 2 and 3 are not separated by the old set partition. 5 is completely isolated, but here we have a nice big block. 6. So if I had drawn this properly, this 8 would be a little outside this, and I would have a clear path from 8 to 7, 7 to 6, 10 to 6. So what I get is the new set partition has a block 1, 4, 2, 3, 5 is in a block all by itself, then 6, 7, 8, 10, and 9. So this I define to be a function which I'll call phi. So phi, as described here, is an order reversing bijection. The point is that if you were to club two blocks of your blue set partition, then you would end up separating blocks of the red set partition. So if I were to club, for example, this 1, 5, 6 with 2, 4, then I would end up having the convex hull would separate 1 and 4. And so I'd end up splitting up a block or maybe multiple blocks of the red set partition. So clubbing blocks in the blue set partition will be splitting blocks in the red set partition, and splitting blocks in the red partition may allow blocks of splitting blocks of the blue set partition may allow blocks of the red set partition to merge. And this is why phi is an order reversing bijection. And this symmetry is evident here in this picture of non-crossing set partitions of 4. What's more is that this bijection I've defined it actually reverses the layers of this set partition. So what are the layers? So this top layer is the only set partition with just one block. The next layer consists of set partitions with two blocks. The next layer consists of set partitions with three blocks, and the last layer is set partitions with four blocks. Now here I'm looking at set partitions of 10, so they can have anything between 1 to 10 blocks, and so here the total number of blocks is 1, 2, 3, 4, 5, 6, and here the total number of blocks should be 5. 1, 2, 3, 4, 5. The complementary number of blocks. So the number of blocks in set partition X and the number of blocks in phi X, they will add up to n plus 1.